Hello friends, IBM is here with another episode of Learning Physics, and this is all about past paper questions. That is, we are concentrating on quantum physics, that is Physics 9702 Cambridge, advanced level structured questions. We are dealing with the solved past paper questions, and this is actually paper 4. I think this is part three of the video, part three of quantum physics. And do not forget, throughout this video, we shall be discussing photon energy, questions about photon energy. We shall be discussing photoelectric emission, questions about photoelectric emission, questions about the wave particle duality, questions about momentum of a photon, and lastly the electron energy level. So in quantum physics, basically the questions rotate about those five areas. Without wasting time, allow me go to the past paper questions. That is the document which has our past paper questions. And I think we must have stopped on page 492 in part 2. So let part 3 start from page 492 still. White light passes through a cloud of cool, low-pressure gas as illustrated here. For light that has passed through the gas, its continuous spectrum is seen to contain a number of dark lines. Use the concept of discrete electron energy levels to explain the existence of these dark lines. I think we answered a similar question, only that maybe we never went into much details. So we mentioned that actually energy levels of electrons are specific, are discrete. An electron in an atom will only absorb a photon whose energy is the difference between two energy levels which are actually allowed. You will notice that the darker lines seen in a continuous spectrum are going to be separated, which means they do not overlap, which therefore means that the energy levels are going to also be separated. Remember, each darker line is going to correspond to a frequency or a wavelength. And since the lines are separated, it means the energy levels are going to be separated. And remember, when an electron absorbs a photon, the electron gets excited, and on the excitation, these photons are emitted randomly in any direction. So it means a certain part of the beam may not be emitted or re-emitted in the same direction as the incident beam. Such photons which are not re-emitted in the same direction as the incident beam going through the cool gas will therefore be missing photons or missing wavelengths on the screen of the continuous spectrum. Okay, so a photon gives its energy to an electron. A photon gives its energy to an electron. A photon gives its energy to an electron, let's say in an inner shell. We use some chemistry in an inner shell. So the electron moves from lower to higher energy level. The electron moves from a lower to a higher. to a higher energy level. So it means the photon is actually excited. The electron is actually excited. Remember, the photon energy which is absorbed or which is taken in by the electron must be equal to uh, the difference in two energy levels. So we can say the photon energy is equal to the difference photon energy is equal to the difference in energy levels or in two energy levels. So a photon whose energy is the difference in two electron energy levels, that photon is going to be absorbed. So that the electron moves from a lower energy level to a higher energy level. The electron, remember, in this case is excited. Then on the excitation, on the excitation, the electrons give off photons of the same energy, but randomly in all directions. So when the excitation occurs, the electrons will now give off the photons which they absorbed randomly in all directions. This means a part of the photons, when re-emitted, may not be re-emitted in the same direction as the incident beam of light. Therefore, such photons will be missing, their wavelength will be missing, and this corresponds to the dark lines. Okay. An electron at rest has mass ME and charge negative Q. A positron is a particle that at rest has mass ME and charge positive Q. A positron interacts with an electron. The electron and the positron may be considered to be at rest. The outcome of this interaction is that the electron and the positron become two gamma ray photons. That is annihilation. Each having the same energy. Calculate for one gamma ray photon the photon energy. So remember, the electrons become the two positron, the positron and the electron become two gamma ray photons. That means the energy of the electron and the positron, that is twice mc squared, m is c squared, becomes twice, or two gamma ray photons. So the two has cancelled, so I'll just simply say that the energy of a single photon, which is hf, is simply going to be mc squared. So I'll just substitute this. This will be 9.11 times 10 power negative 31, then times 3.0 times 10 power 8, and this is squared. So I can check my calculator. So from my calculator, I have this as 8.2 times 10 power negative 14 joules. Then the momentum of a photon, so momentum of a photon is actually energy over c, or it is h over lambda. So momentum can be energy over c, or it can be h over lambda, or momentum is h over wavelength. I'll just use E over c because I have the energy of a photon, so this will be 8.2 times 10 power negative 14 divided by c, which is 3 times 10 power 8. So from my calculator, the energy is the momentum is 2.7 times 10 power negative 22 Newton seconds. State and explain the direction relative to each other in which the gamma photons are emitted. Of course, the gamma photons, remember, they said the electron and the positron may be considered to be at rest. A positron is a particle that at rest has that mass. A positron interacts with an electron. The electron and the positron may be considered to be at rest. That means if they are at rest, their total momentum was zero. If two gamma ray photons are emitted, they cannot move in the same direction, so they must move in opposite directions so that the momentum is conserved, because the gamma photons have momentum. So since momentum must be conserved, they must move in opposite directions so that the total momentum is actually zero. So we can simply say momentum must be conserved in the interaction. Momentum must be conserved in the interaction. And since total momentum before is zero, it means that the momentum of the photons, or I'll use momenta, the momenta of the photons must be equal and opposite. So the momentum of the photons which are created after must be equal and opposite. So it means the photons are emitted in opposite directions. So photons are emitted in opposite directions. So photons are emitted in opposite directions with, of course, with equal but opposite momentum. Total momentum still remains zero, because according to the principle of conservation of momentum, the total momentum of an isolated system of interacting bodies should always remain constant. So the total momentum should be zero, because it was zero before. The structure of a copper crystal is to be examined using electron diffraction. Electrons, having been accelerated from rest through a potential difference V, are incident on the crystal. The de Broglie wavelength of the electrons is 2.6 times 10 power negative 11 meters. Calculate the accelerating PdV. Calculate the accelerating PdV. So we know that the de Broglie wavelength is the wavelength associated with a moving particle. So we know that momentum P is equal to h over wavelength, and we know that momentum is also mass times velocity. So we can use this expression to find the accelerating PD, because we can first find the speed here. So the speed is going to be equal to h, which is 6.63 times 10 power negative 34. We divide this by m times lambda, or lambda times m, and lambda is 2.6 times 10 power negative 11, then times m, which is actually 9.11 times 10 power negative 31. That is the mass of the electrons. So this is going to give us the speed of the electron. I'll just check my calculator here. And it gives me 2.8 times 10 power 7 meters per second. That is the speed. Now, remember the kinetic energy EK is equal to the charge times the accelerating PD, which is a half mv squared. So we have the speed. So we can just make it capital V the subject. The accelerating PD is going to be the mass, which is 9.11 times 10 power negative 31. The speed is 2.8 times 10 power 7, and this is squared. Divide by 2 times the charge, which is 1.6 times 10 power negative 19. So I'll just press my calculator. So this gives me 2.2 times 10 power 3 volts. 2.2 times 10 power 3 volts. Figure 2.1 gives information on 3 lines observed in the emission spectrum of hydrogen atoms. Complete the figure by calculating the photon energy for the wavelength of 486 nanometers. So we want photon energy. Energy of a photon is equal to hc divided by wavelength. H is 6.63 times 10 power negative 31 times 3.0 times 10 power 8 speed of light, divided by the wavelength is 486 times 10 power negative 9 to change it to meters, and we can press our calculator. So from my calculator, the the energy is 4.09 times 10 power negative 19. So this part here, I will just write 4.09 because the power negative 19 is put there. The figure is a partially completed diagram to show energy levels of a hydrogen atom. So we have L, we have 3.03 times 10 power negative 19. Okay. On the figure, draw one further labeled energy level, and complete the diagram with the arrows to show the energy changes for the other two wavelengths. Of course, the energy we have calculated is above the one we have there, but the separation, the change, the wavelength, you see that the wavelength is actually very small. The change in wavelength is relatively smaller than this one here, so it means the second line is going to be closer. The second line is going to be closer to the energy level of 303. So I'll put it around here. So this is going to be 4.09 times 10 power negative 19 joules. And then the two possible transitions. Draw one further labeled energy level. I've drawn that one. And complete the diagram with the arrows to show the energy changes for the other two wavelengths. So we have one wavelength. So the other two wavelengths, there is one possibility of this being, this transition is very possible. And this transition is also very possible. So I will draw those two wavelengths. So those are the possible two wavelengths here. Of course, this is just a typing error. This is supposed to be nanometers, not millimeters. Because you see here it is given as 656 nanometers. Okay, so those are the two energy, these are the two possible transitions or possible wavelengths. We have drawn the energy level that is further labeled energy level as required. Explain what is meant by photon. So we are now familiar with the photon as being quantum of energy of electromagnetic radiation or a packet of energy. A photon is a packet of energy of electromagnetic radiation. Packet of energy of electromagnetic radiations, and energy is equal to H times F. The photoelectric effect provides evidence for the particulate nature of electromagnetic radiation. State three experimental observations that support this conclusion. Of course, these ones we have mentioned, that there are five. We can always mention them. Number one, instantaneous emission. Instantaneous emission of electrons. We say that there is no time delay between illumination and emission of electrons. Number two, we say that the maximum kinetic energy, maximum kinetic energy of electrons is independent of intensity. Number three, we know that the maximum kinetic energy of electrons depends on frequency. Depends on frequency. Number four, we know that, of course, intensity will therefore just affect the photoelectric current produced or the rate of emission. So you can say the rate of emission of electrons is directly proportional to intensity or depends on the intensity, or we can simply say that the photocurrent depends on intensity. Photocurrent depends on intensity. Photocurrent depends on intensity. Number 3 or number 5, remember there is a certain threshold frequency below which no photoelectric emission occurs. So there is a threshold frequency below which no electrons are emitted. So that is actually, those are just those are some of the evidences which are provided by the particulate nature of electromagnetic radiations. You can only state 3 of them. Electromagnetic radiation of wavelength lambda and intensity I, when incident on a metal surface, cause n electrons to be ejected per unit time. The maximum kinetic energy of the electrons is Emax. So it means n is the number of electrons emitted per unit time. The maximum kinetic energy is Emax. State and explain the effective n on n and Emax when the intensity is reduced to half I, but the wavelength lambda is unchanged. Of course, when the wavelength is unchanged, it means the photon energy has not changed. But since the wavelength is reduced, it means that the wavelength is reduced to half of I. It means that now fewer photons are incident onto the metal plate, and therefore the number of electrons emitted per unit time is also going to be halved. So we can say photons have the same energy, so Emax is unchanged. The photons have the same energy. So Emax is unchanged. So the maximum kinetic energy does not change because the wavelength is not changed. But the number of photons per unit time is halved. Therefore, the number of electrons per unit time is also halved. The number of electrons since the intensity has been halved, then the number of electrons emitted per unit time is also going to be halved. In other words, the photocurrent is going to be halved. Part 2, the wavelength is reduced, but the intensity is not changed. Remember, reducing the wavelength implies increasing the frequency. And increasing the frequency means photon energy has been increased. If the intensity does not change and yet photon energy has been increased, it means we shall now have fewer photons incident on the surface per unit time, which means we shall now have fewer electrons emitted per unit time because each electron interacts with a single photon. So photons have higher energy. Photons have higher energy or higher, okay, photons have higher energy Photons have higher energy, so it means Emax increases. So Emax increases. Photons have high energy, so Emax increases, but fewer photons per unit time, so N decreases. But we have fewer photons incident on the surface per unit time. Fewer photons per unit time, so N decreases. Fewer photons incident on the surface per unit time will imply fewer electrons emitted. In part A, we saw that the intensity was reduced, but the wavelength was unchanged. So the number of photons incident was reduced to half, so the number of electrons per unit time had also to be halved. But when the wavelength is reduced, frequencies increase. That means photon energy is higher. But if the intensity does not change, then it means only a few photons can be incident on a given area per unit time. So N decreases. Okay. State an effect, one in each case, that provides evidence for the wave nature of particles. For the wave nature, we say that if particles can show diffraction, then they are behaving as a wave, because diffraction is a property which is strictly shown by waves. So the wave nature is explained by the electron diffraction. Electrons are considered to be particles, but they can show diffraction, which is a property of waves. So that is electron diffraction. Then the particulate nature of electromagnetic radiation. There are two basic properties. The first one is photoelectric effect. Photoelectric effect. Photons can knock out electrons from a metal surface. That is photoelectric effect. Number two is Compton effect or Compton scattering. So a photon collides with an electron and it gives some energy to the electron. So the photon loses some energy as the electron gains some energy. That's what we call Compton scattering. So they move at several at different angles after that interaction. Okay. Four energy levels in an atom are shown here. An emission spectrum is associated with the electron transitions between these energy levels. For this spectrum, state the number of lines. So since the emission spectrum is associated with all these, then I will start with the highest energy level to the lowest energy level. So that is one line. Then I will still with the highest. Those are two lines. Still with the highest. Those are three. So I'm done with the highest. These are three lines originating from the highest. Then the next energy level. So this next energy level is this one. So I will start this. That is one, and with the same, that is two. So these are two lines also for the second energy level. And lastly, the last energy, starting with the third excited or the first excited state. Starting with the first excited state. So this is another line. So no line has been left out, and you realize that there are 1, 2, 3, 4, 5, 6 lines. So the number of lines is actually 6. So there are 6 lines, 6 possible lines there. State the number of lines. We have finished to state the number of lines. Calculate the minimum wavelength. Minimum wavelength Of course, wavelength is minimum when frequency is maximum, and frequency is maximum when energy is maximum. So to find minimum wavelength, we need the maximum change in energy. So our wavelength is going to be equal to hc divided by change in energy, and this is going to be actually 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by the energies. The highest change in energy is going to be from negative 0.87 to negative 5.44. So I'll subtract those two energies. Negative 0.87 minus negative 5.44 times 10 power negative 19. So from my calculator, I'm getting this as 4.4 times 10 power negative 7. 4.4 times 10 power negative 7, I think that is close to violet. By reference to the photoelectric effect, state what is meant by threshold frequency. So threshold frequency, that is the minimum frequency of electromagnetic radiations radiation the minimum frequency of electromagnetic radiation needed for an electron to be emitted from a surface or required to emit or to release an electron from a metal surface. That is threshold frequency. The minimum frequency required to release an electron from a metal surface, that is threshold frequency. The minimum frequency below which no electron is released from a metal surface. Minimum frequency of electromagnetic radiation below which no electrons are emitted from a metal surface, that's work function. The surface of a zinc plate has a work function of 5.8 times 10 power negative 19 joules. In a particular laboratory experiment, ultraviolet light of wavelength 120 nanometers is incident on the zinc plate. A photoelectric current I is detected. In order to view the apparatus more clearly, a second lamp emitting light of wavelength 450 nanometers is switched on. No change is made to the ultraviolet lamp. Using appropriate calculations, state and explain the effect on the photoelectric current of switching on this second lamp. Okay, so first of all, we need to find the threshold wavelength. We need to find the threshold wavelength. We can use the threshold wavelength, or we can find the energies. We can find the energy of energy correspond to the wavelength. The energy correspond to the wavelength of the second lamp, so that we see if it is greater than the work function. If it is not, then there is no emission, so it has no effect. So the easiest is to find the threshold wavelength. Work function energy phi is equal to h f naught, which is equal to h c over lambda naught. I'm trying to find lambda naught threshold wavelength, which is going to be 6.63 times 10 power negative 34 divide by, or times 3 times 10 power 8 divide by the work function energy, which is 5.8 times 10 power negative 19. I'm straight away going to convert this into nanometers, so I'll say times or divide by 10 power negative 9 to change it to nanometers. This last part here is to change it to nanometers because the wavelengths given there in nanometers. So here I'm getting approximately 340 nanometers. So this is the threshold wavelength. If the wavelength is above this threshold, there is no emission of electrons. So you notice that 450 nanometers is greater than the threshold, so it has no effect. So I can simply say from this point that 450 nanometers is greater than the threshold wavelength, so there is no effect. So no effect. So no effect. That's number one. Number two, I could find the energy corresponding to 430. I mean 400 or I would get the frequency corresponding to 450 nanometers and compare it with the threshold frequency. Or I get the energy corresponding to 450 nanometers and I compare it with the work function. So let's check. The energy corresponding to that photon, the energy of the photon. This is another alternative. Energy of the photon is going to be hc over lambda, which is 6.63 times 10 power negative 34 times 3 times 10 power 8 divide by the wavelength, which is 450 times 10 power negative 9. So this gives me energy as 4.42 times 10 power negative 19 joules. You see that this energy is less than the work function. So still emission cannot occur because work function is the minimum energy required for an electron to be released. So we can say photon energy is less than the work function. So no effect. Because the photon energy is less than work function, it cannot cause emission of any electrons. Alternatively, we can find a frequency corresponding to the same wavelength. If that frequency is less than the threshold, of course, the threshold can be got from this work function. I think I can show that method also here. Method number 3, let's find the threshold frequency. Remember, work function is equal to h times threshold frequency, which means the threshold frequency is going to be work function, which is 5.8 times 10 power negative 19 divided by 6.63 times 10 power negative 34. So this is method number 3. So this is giving me a threshold frequency of 8.7 times 10 power 14 hertz. That is threshold frequency. Let's check the frequency correspond to 450 nanometers. So frequency is going to be C over lambda, which is 3 times 10 power 8 divided by lambda, which is 450 times 10 power negative 9. So frequency correspond to that wavelength is 6.7 times 10 power 14 hertz. So you see that the frequency of the photon is less than the threshold frequency, so there is no effect. The frequency of the photon is less than the threshold frequency, so there is no effect. So you can choose whatever way you want to explain your answer, as long as you show some work. Explain how the line spectrum of hydrogen provides evidence for the existence of discrete electron energy levels. How the line spectrum, not that each of the lines are separated and each line corresponds to a specific wavelength, which corresponds to a specific energy, a specific energy or specific frequency, and it implies that there is only a specific change of energy, and if there is only a specific change, it is only because there are specific energy levels. That is when specific energy levels are the one which allow specific energy changes. Okay, so each line represents photon of specific energy, frequency, or wavelength. Each line represents a photon of specific energy or wavelength or frequency. Remember, energy is equal to hf, which is hc over lambda. So when I say specific wavelength, specific frequency, specific energy, that is the same thing. So each line represents a photon of specific energy, wavelength, or frequency. A photon is emitted as a result of energy change. A photon is emitted as a result of energy change, of an electron. A photon is going to be emitted when there is energy change of an electron, and only specific energy changes occur. Specific energy changes means discrete energy levels. So a photon is only emitted when the energy of the electron as a result of an electron. What did I say? A photon is emitted as a result of energy change of an electron, as a result of energy change of an electron. Specific energy changes implies discrete energy levels. So each of those lines represent a photon of specific energy. or specific wavelength or frequency, and the photon is only emitted whenever there is a change in a photon is emitted when an electron changes its energy or the energy of the electron changes. Since we have specific energy changes, these imply discrete energy levels. Some electron energy levels in atomic hydrogen are illustrated here. We see the highest is negative 0.85, negative 1.50, and negative 3.40. Two possible electron transitions A and B giving rise to an emission spectrum are shown. These electron transitions cause light of wavelength 654 and 488 nanometers to be emitted. On the figure, draw an arrow to show a third possible transition. Of course, the third one is easier to see. The third possible transition must be from negative 0.85 to negative 1.50. Negative 0.85 to negative 1.50. So that is the third possible transition. Calculate the wavelength of the emitted light for this transition. So our wavelength, of course, wavelength is simply going to be hc divided by the difference in energy. This is going to be 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by the change in energy. It is going to be between 0.85 and 1.50, so I'll say negative 0.85 minus negative 1.5, and in electron volts, so I will say times 1.6 times 10 power negative 19 to change it to joules. So this is 1.9. I'm getting 1.9 times 10 power negative 6 meters. 1.9 times 10 power negative 6 meters. You can also check. The light in a beam has a continuous spectrum of wavelength from 400 nanometers to 700 nanometers. The light is incident on some cool hydrogen gas as illustrated here. So incident light, cool hydrogen gas, emergent light. So incident light, they are telling us to using the values of wavelength in B, state and explain the appearance of the spectrum of the emergent beam. So we have seen the possible transitions, and we have seen A and B can be possibly be, they give rise to an emission spectrum. So we could be, if these are re-emitted randomly, since they can be absorbed, if they are re-emitted randomly, then they could appear missing in the emergent beam. So we could expect two darker lines. We could expect two darker lines in the emergent beam if they are re-emitted randomly. So we can say a continuous spectrum with two dark lines is observed. A continuous spectrum with two dark lines. Is observed. Why only two? Remember, light is within this wavelength and this one. And we have seen that we had light, the transitions were for this wavelength and this one, which is in the range. This third transition here, we see that is not within the range. This is, when I change this to nanometers, I will divide that by 1.9 exponent negative 6 divided by exponent negative 9. This is 1900 nanometers. 1900 nanometers, and 1900 nanometers is outside this range. Therefore, that transition is not that one will not be observed within this range. So we only have the two, because the two, one was 488, another one was 655, which are in that range. So we expect that there could be a continuous spectrum which has two darker lines observed in it. And why do we have these darker lines? Electrons in a gas absorb some photons, and they absorb only those photons whose energy is equal to 2 at the difference between two energy levels. On de-excitation, the light photons are re-emitted in all directions, and they could be missing from the emergent light beam. So we can say that electrons in gas absorb electrons in gas absorb photons with energies equal to, let me call them excitation energies, with energies equal to the excitation energies. And when I talk about excitation energies, I'm referring to difference in energy levels. So electrons in gas absorb photons with energies equal to excitation energies. When somebody talks about those excitation energies, he's referring to the energies which are equivalent to difference in two energy levels. So on the excitation, light photons are re-emitted in all directions. When the electrons de-excite to re-emit the photons which they had absorbed, then they re-emit them randomly in all directions. So there is a possibility that such photons are not re-emitted in their original direction. So they would be missing in the spectrum formed on the screen, which gives us those two dark lines. An experiment of the photoelectric effect includes the terms photon energy and work function. Explain what is meant by a photon. So a photon is a packet of energy of electromagnetic radiation. Photon is a packet of energy of electromagnetic radiation, and we know that energy is equal to h times f. It depends on the frequency. Then the work function, we know that the work function is the minimum energy of electromagnetic radiation required to cause emission of an electron from a metal surface. Below this energy, no electron is emitted. So the minimum energy of electromagnetic radiation required to cause emission of an electron from a surface. Required to cause the emission of an electron from a metal surface, that is work function. Below this minimum energy, below this work function energy, no electrons can be emitted. In an experiment to investigate the photoelectric effect, a student measures the wavelength lambda of the light incident on a metal surface and the maximum kinetic energy Emax of the emitted electrons. The variation with Emax of 1 over lambda is shown in the figure below. Okay, so we have 1 over lambda and Emax. I may want to draw this line until it touches the x-axis. I may just want to extrapolate it because I know some of the questions may need the same. Okay, so I can extrapolate that line. Then see the questions. The work function energy of the metal surface is phi. State an equation in terms of lambda, phi, and Emax to represent conservation of energy of the photoelectric effect. For the photoelectric effect, explain any other symbols you use. Of course, remember energy of the photon, part of it becomes the work function and part of it becomes maximum kinetic energy. But energy of the photon is given by HF. Work function is HF naught plus Emax. We want it in terms of wavelength. F is c over lambda, so this is hc over lambda, hc over lambda naught plus Emax. So the equation which they want, they want it in terms of phi, so I will leave this is phi. So we want the equation will be hc over lambda is equal to phi plus Emax. The only new symbol which is not mentioned here is c, so I'll say c is the speed of light. Even h is not mentioned, h is Planck's constant. H is Planck's constant. Use your answer in Roman 1 and figure 7.1 to determine the work function energy phi of the metal surface. Work function energy of the metal surface. So the easiest way to look at this is maybe to look for a point where Emax equals to let me look for a point where Emax is, or where 1 over lambda becomes 0. What happens from this equation here? Hc over lambda, work function, remember, is equals to work function plus Emax. At a point where 1 over lambda equals to 0, for 1 over lambda equals to 0, what is Emax? Of course, the left will be 0. What is Emax from the graph? Emax is going to be negative 4.0 times 10 power negative 19. It is power negative 19. So Emax is going to be equal to negative 4.0 times 10 power negative 19 joules. So what does that mean? And remember, when 1 over lambda is 0, phi is equal to negative Emax. So it means when 1 over lambda is 0, phi is equal to negative Emax. And Emax is negative 4.0. So phi is going to be negative of the negative, which becomes negative of negative 4.0 times 10 power negative 19 joules, which gives us 4.0 times 10 power negative 19. So I just use the graph. When 1 over of lambda is 0 becomes 0, Emax is negative 4.0 times 10 power negative 19. But when the left becomes 0, Emax becomes negative, phi becomes negative Emax. Okay. Then 2, a value for the Planck constant. We are still using the figure, the answer in Roman 1 and the figure 7.1 to determine the value for Planck constant. Note that a graph of 1 over lambda is plotted against Emax. A graph of 1 over lambda is plotted against Emax. So if I make 1 over lambda the subject from that equation, I have that 1 over lambda is equal to phi divided by hc plus 1 over hc times Emax. I just made 1 over lambda the subject. And if I compare this equation with the equation of a straight line, that is y equals to mx plus c, so this one will be c plus mx. On the x-axis, I have Emax. On the y-axis, I have 1 over lambda. So you see that the gradient is equal to 1 over hc. So I'll simply say that the gradient equals to 1 over hc. Let's find the gradient. Let's try to find the gradient of this line. So the gradient I'm looking for precise values. For example, this is fine. Okay, so that is one value. Okay, I can take this one. So I'm finding the gradient. I'll just work out from this grid. So the scale on the vertical, I think, is 0.1. So this is 3, 3.1, 0.2, 0.3, 0.4, 0.5, 3.5. So that is 3.5 minus, this is 2.1, 0.2, 0.3, 0.4, 0.5. So this is minus 2.5. On the vertical axis, that is times 10 power 6 divided by, on the x-axis, the scale is also 0.1, so this is 1.1 The other one is 3.1. So this is 3.1 minus 1.1 times 10 power negative 19. You can use different points for the gradient. So I'm finding the gradient there, so that is 3.5 minus 2.5 divided by 3.1 minus 1.1. So my gradient is 5.0. You can also check yours. So my gradient is 5.0 times 10 power negative power 24, actually not negative. 5.0 times 10 power 24. So that is my gradient. Divide, so I want to make h the subject. So it means h is going to simply be 1 divided by the gradient times c. So it is 1 over 5.0 times 10 power 24 times c, which is 3 times 10 power 8. So we have 5 exponent 24, 3 exponent 8, 1 divided by the answer. So this gives me 6.67. So this is 6.67 times 10 power negative 34. 6.67 times 10 power negative 34. You can also verify. You may not get exactly the same gradient as I got. It will depend on the choice of points. My points have given me 5.0 times 10 power 24 as the gradient. 5.0 times 10 power 24. You can check yours. State what is meant by a photon. A photon is a packet of energy of electromagnetic radiation. And energy equals to hf. It has been observed that where photoelectric emission of electrons takes place, there is a negligible time delay between illumination of the surface and emission of an electron, that is instantaneous emission. State 3 other pieces of evidence provided by the photoelectric effect for the particulate nature of electromagnetic radiation. So we have already mentioned them, and by now you should be familiar with most of them. Number 1, there is a threshold frequency. Below which no emission occurs. Number 2, we know that the rate of emission of photocurrent is directly proportional to intensity. The rate of emission is directly proportional to intensity. Number 3, maximum kinetic energy of electrons depends on frequency. maximum kinetic energy of electrons does not or is independent of, to be specific, is independent of intensity. So the maximum kinetic energy is independent of intensity. So those are the other four, because the first one of them, instantaneous emission, has been mentioned. Remember to write in full maximum kinetic energy, not writing max Ke. The work function of a metal surface is 3.5 electron volts. Light of wavelength 450 nanometers is incident on the surface. Determine whether the electrons will be emitted by the photoelectric effect from the surface. So we have to find, first of all, the energy of the electrons. I mean the energy of the photon, whose wavelength is 450. So energy is equal to Hc over lambda. So this will be equal to 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by 450 times 10 power negative 9 to change it to to meters. I will now change this to electron volts by dividing by 1.6 times 10 power negative 19. Check with my calculator. So from my calculator, I'm getting this as 2.8 electron volts. Now the question is determine whether electrons will be emitted by photoelectric effect from the surface. The work function is 3.5. Remember, the work function is the minimum energy below which no electrons are emitted. So we notice that 2.8 volts, or the energy of the photon, 2.8 electron volts, is less than the work function. So no emission. Because the energy of the photons of light is less than the work function, we don't expect any emission. State what is meant by the de Broglie wavelength. So de Broglie wavelength, that is the wavelength of a moving particle or the wavelength associated with a moving particle. The wavelength associated with a moving particle, that is the de Broglie wavelength. And we know that the de Broglie wavelength is equal to h over p. An electron is accelerated from rest in a vacuum through a potential difference of 4.7 kilovolts. Calculate the de Broglie wavelength. So we know that the de Broglie wavelength lambda is equal to h over momentum. We also know that kinetic energy Ek is equal to a half mv squared, which kinetic energy is equal to the charge times the accelerating PD. The charge of the electron times the accelerating PD. So it means m squared v squared is going to be twice qv times m. I just multiplied both sides of that equation by m, and this is going to be momentum squared. Momentum squared is equal to twice qv times m. So we know the Planck's constant, we know the charge, and we know the accelerating PD. So therefore we can just now substitute. So the de Broglie wavelength lambda is going to be h over the square root of twice qv times m, which is going to be 6.63 times 10 power negative 34 divided by the square root of 2 times the charge, which is 1.6 times 10 power negative 19 times the accelerating PD, which is 4.7 kilovolts, that is 4,700, then times the mass of an electron, which is 9.11 times 10 power negative 31. I'll press the calculator just once. If your mathematics is not very good, you can first find the momentum, then you now substitute. So this gives me 1.79 times 10 power negative 11 meters, or approximately 1.8 times 10 power negative 11 meters. By reference to your answer in Roman 1, suggest why such electrons may assist with an understanding of crystal structure. You notice that the wavelength here, in comparison with the interatomic spacing, which is 10 power negative 10 meters, it's like the wavelength, the de Broglie wavelength is approximately the same as the interatomic spacing. That means the electrons are most likely to undergo diffraction when passed through the space between atoms. Therefore, since they undergo diffraction, then they can be used in um, studying or understanding crystal structures. So we can simply say that the wavelength of the wavelength, let me say, is of the wavelength is of almost the same order as the separation of atoms. The wavelength is of almost the same order as the separation of atoms, so it can be used in electron diffraction. Okay, so such electrons, a wavelength is of almost the same order as separation of atoms, so this can be used. Let me make this one clear. So that people not think So this can be used in electron diffraction. Okay. Electrons traveling at a speed v in a vacuum are incident on a very thin carbon film as illustrated here. The emergent electrons are incident on a fluorescent screen. A series of concentric rings is observed on the screen. Suggest why the observed rings provide evidence for the wave nature of particles. Why do the observed rings, of course we saw this question earlier on, that when the electrons go through the thin carbon film, they form concentric rings as their diffraction patterns. So the concentric rings are actually evidence of diffraction. Concentric or the concentric circles or the concentric rings are evidence of diffraction. The concentric rings are evidence of diffraction, and diffraction is a wave property. The concentric rings are evidence of diffraction, but we know that diffraction is a wave property. Okay, the initial speed of the electrons is increased. State and explain the effect, if any, on the radii of the rings observed on the screen. When the speed is increased, remember the Broglie wavelength is equal to h over p, which is h over mv. When the speed is increased, it means the momentum is increased, so the wavelength must be decreased. And if the wavelength decreases, then it means the radii of the concentric circles are actually dependent on the wavelength. So the radii is going to decrease. So it's a speed increases, the speed increases, so momentum increases. And from lambda equals to h over p, so wavelength, the de Broglie wavelength decreases. If you want to look at these diffraction patterns, n lambda is equal to actually, if n lambda is equal to d sine theta, it means the diffraction angle is actually going to reduce when lambda decreases. So it means the radius also increases after even the circumference has reduced. So from lambda is equal to h over p, so wavelength decreases, hence radii decreases. When I say radii, that is plural. The radii decrease. So that is the consequence of increasing the speed of the electrons. A proton and an electron are each accelerated from rest through the same potential difference. Determine the ratio de Broglie wavelength of the photon over de Broglie wavelength of the electron. Okay, so we know that because they are accelerated from rest through the same PD, they have the same they will have the same kinetic energy. So the electron and the proton are going to have the same kinetic energy. Why? Because the kinetic energy is equal to charge times accelerating PD. Because they have the same charge, 1.6 times 10 power negative 19 in magnitude, and they're accelerated through the same PD, so they have the same kinetic energy. And remember, we saw that kinetic energy EK is equal to a half mv squared, which is equal to E, or charge, times accelerating PD. When we multiplied both sides by m, we saw that m squared v squared was equal to twice qv times m. I multiplied both sides by m, so momentum was there for the square root of twice q accelerating PD times m. So that is the momentum. We want de Broglie wavelength. So we want the ratio, which is momentum of the proton, de Broglie wavelength of the proton. Okay. We want the de Broglie wavelength of the proton over the de Broglie wavelength of the electron. So I will say lambda for proton over lambda for electron. And remember, de Broglie wavelength, lambda is h over momentum. So the ratio is going to be equal to, for proton, it is going to be h over momentum of a proton, which is square root of twice q. V is the same mass of the proton. Divide by, I get the reciprocal, the square root of, I'm dividing with the electron, which will be twice charge of the electron, PD, accelerating PD, mass of the electron, then divide by h. So you notice that for the ratio, h cancels, h has cancelled, 2 has cancelled, q has cancelled, v has cancelled, and I've only remained with the square root of the mass of the electron divided by the mass of the proton. So it means the ratio is going to be equal to the square root of the mass of the electron, 9.11 times 10 power negative 31, divided by 1.67 times 10 power negative 27. That is the mass of the proton. So this gives me 2.3 times 10 power negative 2. 2.3 times 10 power negative 2 as the ratio. Okay, next. By reference to the photoelectric effect, explain what is meant by work function. So we now know that work function is the minimum energy of electromagnetic radiation required to remove an electron from a metal surface. From a metal surface. Minimum energy of electromagnetic radiation required to remove an electron from a metal surface. That is work function. The minimum energy of electromagnetic radiation below which no electron can be released from a metal surface. By reference to the photoelectric effect, explain why even when the incident light is monochromatic, the emitted electrons have a range of kinetic energy up to a maximum value. Remember, it is the surface electrons which have maximum kinetic energy, but some electrons reside below the surface, so energy is required to bring them to the surface. So we simply say maximum kinetic energy is when an electron is ejected from the surface. So all the surface electrons have maximum kinetic energy. Maximum kinetic energy is when an electron is ejected from the surface. Energy is going to be lower than maximum because energy is required to bring electrons to the surface. So such electrons which reside below the surface, part of the photon energy is wasted in bringing them to the surface. So what remains to give them kinetic energy is going to be smaller than the maximum. That's why the energy will have a range of values. There will be a range of kinetic energies up to a certain maximum value. Remember, it is the surface electrons which have maximum energy because for them, they require very little energy to set them free. They are almost free. So too much surplus energy becomes kinetic energy for such surface electrons. Electromagnetic radiation of frequency f is incident on a metal surface. The variation with the frequency f of the maximum kinetic energy, E max of electrons emitted from the surface, is shown in the figure here. Okay, so I will immediate, of course, I always know that you will always need to extrapolate this line if you are to use the graph. Extrapolating the line so that it cuts the x-axis. Okay, so use the figure to determine the work function energy of the metal surface. Of course, I know work function is equal to H times F naught. All that I need is F naught. So H is 6.63 times 10 power negative 34 times F naught, which is 1.0. This is going to be F naught. 1.0 times 10 power 15 because the power of 10 is 15. I just check on my calculator. So this is going to be 6.63 times 10 power negative 19 joules. The second metal has a greater work function energy than that in Roman 1. Draw a line to show the variation with the frequency with F of Emax for the metal. Because it has a greater work function, we see that work function is directly proportional to F naught. If the work function is greater, then also it means that F naught is also going to be higher. So I'm just going to choose a higher value of work function and I draw the graph. So I will draw the graph on the right hand side of the current graph. The lines are parallel because remember the gradient is independent of, the gradient is always a constant. So I will just draw a line which is parallel to one which is already there on the left, on the right. Okay, the lines should be extremely parallel because remember the gradient is going to be, the gradient is hc and this is a constant. So the gradient is constant. Explain why the graphs in Roman 1 and 2 do not depend on the intensity of the incident radiation. In other words, why does maximum kinetic energy depend on frequency but not on intensity? Intensity only determines the number of photons arriving per unit time, which determines the number of electrons emitted per unit time. It does not determine the energy of the emitted electrons. So intensity only determines the number of photons arriving per unit time. Intensity only determines the number of photons arriving per unit time and therefore determines the number of electrons. And therefore determines the number of electrons per unit time. Not energy. It does not determine energy. Intensity does not determine energy. It just determines the number of photons arriving per unit time, which determines the number of photons, the number of electrons emitted per unit time, but not the energy of these electrons or not the energy of the photons. Where white light is incident on a cloud of cool hydrogen gas as illustrated below. Okay, so we say incident white light going through cool hydrogen gas and emergent light. The spectrum of light emerging from the gas is found to contain a number of dark lines. This is the same question that we have answered. Explain why these dark lines occur. We said when light goes through the hydrogen gas, some photons whose energy is equal to the difference between two energy levels are absorbed. The electrons are excited. On de-excitation, these light photons are re-emitted randomly in any direction, which means only a part of the re-emitted light is in the direction, the incident direction or initial direction of the beam. Okay, so we are saying photon energy equal to difference in energy. Photon energy equal to difference in energy of two energy levels. Is absorbed. Is absorbed by an electron. So photon energy, which is equal to a difference in energy of two energy levels, is absorbed. Then on electron excitation, on electron excitation, photons of the same energy, or a photon of the same energy is emitted randomly in any direction. A photon of the same energy is emitted randomly in any direction. So what is the consequence of this? It means only a part of the re-emitted light, only a part of the re-emitted light is in the incident, is in the initial direction of the beam. So because the photons are emitted randomly, a small part of light may not be emerging in the same direction as the incident beam. So photons correspond to that part of light will not be seen on the screen or in the spectrum. So their positions will be represented as darker lines. Some electron energy levels in a hydrogen atom are illustrated here. One dark line is observed at a wavelength of 435 nanometers. Calculate the energy in electron volts of a photon of light of that wavelength. So we know that energy is equal to Hc over wavelength. That is 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by 435 times 10 power negative 9. Change it to meters. And we want the answer in electron volts. Okay, let me first press this. So this is 4.57 times 10 power negative 19 joules. I now change it to electron volts. So energy is going to be 4.57 times 10 power negative 19 divided by 1.6 times 10 power negative 19. And this is 2.86 electron volts. On the figure, draw an arrow to indicate the energy change that gives rise to this dark line. So 2.6, I will just check by adding these energies. 2.6, if I add it to, I'm adding 2.6 to this one and I see if it happens, plus 2.86 What do I get? Negative 3.4 plus 2.86. This gives me negative 0.54. Okay, let me check if I write this. If I check, let me change this, and I see 6.63 exponent negative 34 times 3.3 exponent 8, 435 exponent negative 9 divided by 1.6 exponent negative 19. That is 2.85. Okay, so this is giving me a negative 0.54, but it's supposed to be approximately negative 0.55 instead. Okay, it depends on how you have rounded off here. Let me see, 3.41 minus 2.9. .6. Okay, so this is, I think this is 5. I'm just adding wrongly. Negative 3.41 plus 2.86. It's negative 5.5. So that is the transition. So this being a darker line, I will draw my line going upwards. So that is the transition. I just added this energy to negative 3.41 and it fell at that point. It fell to negative 0.55, not negative 0.54. Sorry about this mathematics. Yeah, my mathematics is very old. Okay, so that is the transition. You could also draw this line going downwards because after all, after that transition, the electron does not take long in an excited state. It will again fall backwards. So you can also draw the arrow pointing downwards. So state what is meant by photons. So a photon is a packet of energy of electromagnetic radiation, and energy is equal to H times F. Packet of energy of electromagnetic radiation and energy is HF. Okay, let's stop on this page. Part B. A beam of light is incident normally on a metal surface, as illustrated here. The beam of light has cross-section area 1.3 times 10 power negative 5 and the power 2.7 times 10 power negative 3. The light has wavelength 570 nanometers. The light energy is absorbed by the metal and no light is reflected. Show that a photon of this light has an energy of 3.5 times 10 power negative 19 joules. Okay, so energy of a photon is equal to hc over lambda. So that is 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by the wavelength is 570 times 10 power negative 9. So from my calculator, I get this as 3.49 times 10 power negative 19, which is approximately 3.5 times 10 power negative 19 joules. Calculate for a time of 1 second the number of photons incident on the surface. So number of photons, of course, this is the energy of each photon, and the power is 2.7 times 10 power negative 3 watts. So that is the total energy per second is that. So the number of photons per second is going to be the power divided by the energy of each photon. So since power is equal to energy over time, it means and energy is number of photons times the energy of each photon times the energy of each photon divided by time. So we want number of photons in 1 second. So it means the number of photons, the number is simply going to be the power, which is 2.7 times 10 power negative 13 divided by the energy of each photon, which is 3 point maybe 5 times 10 power negative 19. From my calculator, this is 7.7 times 10 power 15. Then calculate for a time of 1 second the change in momentum of the photons. Change in momentum. So we know that momentum of a photon is equal to h over wavelength. H is 6.63 times 10 power negative 34 divided by the wavelength, which is 570 times 10 power negative 9. That is going to be momentum of a single photon. So the total change in momentum, this is momentum of a photon. The first one is momentum of a photon. Total change in momentum is going to be now this value here, momentum of one photon, which I want to press the calculator and get. Which is 1.16 times 10 power negative 27 kilogram meters per second. That is momentum of one photon. So total change in momentum is going to be 1.16 times 10 power 27 negative. Then times the number of photons, which is 7.7 times 10 power 15. And this gives us the total change in momentum as 8.96 times 10 power negative 12. Lastly for today, use your answer in B, part 2, to calculate the pressure that the light exerts on the metal surface. So we know by definition, pressure is going to be equal to, okay, I don't want to use P for momentum because we used it here. By the way, P for momentum is a small letter P. Momentum is a small letter P. So pressure, by definition, pressure is equal to force over area. But force, by definition, is the rate of change of momentum. In other words, it is change in momentum with the time divided by area. But the change in momentum with the time is going to be actually the momentum above. So the force is going to be 8.96 times 10 power negative 12 divided by 1.3 times 10 power negative 5. That was given as the area. So I press my calculator. So this gives me 6.9 times 10 power negative 7. So that marks the end of part 3. We meet in the last part, that is part 4, tomorrow. See you and thank you. I hope you enjoyed this video. Thank you, and do not forget to subscribe and download the document which has past paper questions and practice on a hard copy rather than just watching the video. Thank you and stay blessed.